Hello everyone. In this short series of video, we're going to look at some approximation algorithms for the traveling salesman problem, commonly known as TSP. So TSP is an NP-Hardness problem, so let's always keep that in mind. So we cannot find a solution that runs in polynomial time. So what happens is that we try to look for approximation algorithms that can run in polynomial time and that we can use to find some approximate solution for these NP-Hardness problems. In particular, what is the TSP? So the TSP is the traveling salesman problem. Basically, given a graph, in this case, with the TSP, I didn't draw it, but we are usually analyzing a complete graph, meaning that we have one edge going out from each node to each other node. What we want is to find the Hamiltonian tour with the lowest cost. What is an Hamiltonian tour? An Hamiltonian tour is basically a tour that starts, sort of a visit that starts in a particular node, visits all of the other nodes exactly once, and then goes back to the beginning. So, and we obviously want to minimize the cost of doing that. Obviously, the edges, each of those edges has a cost, so it has a positive integer, something like that, and we want to find the tour that has the minimum cost. So this obviously has some very interesting application also in the real world, because for example, a company like Amazon or whatever might want to know what is the path that saves the most fuel, for example, for their salesman to go to sort of do their things. So in input we have, so what is our input? Our input is our graph with some vertex and some edges. It is complete and weighted. And what we, as I said, this is an NP-Hardness problem. So we want to sort of add some extra constraints so that we can find some more doable, let's say, approximation algorithm. So for this approximation algorithm that I'm about to show you, we are going also to assume that for each triplet, so U, V, Z of nodes, so in the vertex, we have that the cost from going to U to Z is always less than or equal than the cost from going to U to V plus the cost from V to Z. So basically what this means in a more, let's say, graphical way is that if we have these three nodes, the cost from going, so the cost of this path is always, for each triplet of nodes, it's always less than, it costs always more than doing this thing. Okay, so this is our extra assumption that we do for this approximation algorithm. So what is the algorithm itself? So the first step is to find T star minimum spanning tree in the graph. So what is a minimum spanning tree? You probably already know, but it is basically, let's sort of draw it here. So it is a tree that covers all of the nodes of the graph with minimum cost. So and we can, there are many algorithms to find the minimum spanning tree on graphs. It's not the topic of this video, but for example, there's the Prim algorithm, there is the Kruskal algorithm, there are just many of them, and they all solve this problem in polynomial time, so we're good. So let's call this T star. So the second step is to double the edges in our minimum spanning tree. Doubling the edges means that we do this thing. So very simple. We just create an extra edge for each pair of nodes. And there's a very specific reason why we do this, is because now we are looking for a so-called Eulerian tour. So now we find Eulerian tour E on G prime. So let's call this thing G prime. So we double the edges, we call this new graph that we obtained G prime, and now we find Eulerian tour on G prime. What is an Eulerian tour? It is a tour that, differently from the Hamiltonian tour that we're looking for, the Eulerian tour goes through each edge once and exactly once. And this is another thing that we can do in polynomial time, and it is it requires some algorithms, for example, the Fleury algorithm or some variation of the DFS. It's not the topic of this video. So the Eulerian tour, for example, in this case, might look something like this. So we just, let's say, start from here, we go there, and we go here, something like this. So very easy, just go through each edge of the graph exactly once. So after we found the Eulerian tour, what we're going to do is the final step of the algorithm, which is use shortcuts to find Hamiltonian cycle H. And what do I mean by that? So what are these shortcuts that I'm talking about? So now that we have this Eulerian tour, remember, we don't care about edges, we care about nodes. So we want to go through each node once and exactly once, and obviously go back to the starting node. So let's say that we start from here. So the Eulerian tour says, okay, go there. Okay, so we do this, we go there, and we visited this. Now the Eulerian tour says go there, so we just keep following. Now it says go here, we keep following. Now the Eulerian tour would say, okay, go back to this node. But as you can see, this node we already visited. We don't want to go there again. So what we're going to do is we're going to use a shortcut to go instead. Instead of going there, we go to the next node. So we go there actually. So this is what we're going to do. We're going to take this shortcut. And what is the shortcut? You're saying there's no edge that makes me go there. But actually, if you remember, in the input of our problem, we had a complete graph, meaning that here I've drawn only the spanning tree, but we have actually one edge for each single pair of nodes. So there is an edge that goes there. It's basically just not part of the spanning tree, but we have an edge that goes there. So we take that edge and go there. Same thing, now instead of going back here that we've already visited, we go to the next, so we would go there, but this is already visited as well, so we go to the next, so we go there. And we take this shortcut. And as you can see now, we've finished our Hamiltonian cycle, Hamiltonian tour. Because we're back to the starting node. So this is simply how this algorithm works. So let's go through it once again. So we find the minimum spanning tree, T star, which is the black one. We double the edges, so the red ones. Then we found the Eulerian tour in G prime. G prime is this new graph that we created with the doubled edges. And then once we found the Eulerian tour, we go through the Eulerian tour, and every time that we would go back to our already visited node, we take a shortcut. And that's it. This is our output. This is our Hamiltonian tour. And as you can see here, we've done all operations that are doable in polynomial time. So we don't, let's say, we're good. We're fine. We found an algorithm that approximates the solution in polynomial time. So the question now is, how bad or how good is this solution? Like, we know that the TSP problem is an NP-hard problem, so there is actually an optimal solution that we don't know anything about. But the cool thing here is that we know for sure that with this algorithm we find a Hamiltonian cycle that in the worst case scenario is twice as bad as the optimal tour. So this is a theorem that we say, so that we want to prove also. So in worst case, we have that the cost of H divided by the cost of H star is lesser equal than 2. So let's say in the worst case is equal to 2, but in general, let's say in general, so in every case, we know that this thing is lesser equal than 2. So in the worst case, it's maximum 2. So we find in the worst case a tour that is twice as long as the optimal one. So this is something that we're going to prove now. So let's do the proof. So let's just get rid of this. And this is why this algorithm is usually called a two approximation algorithm, and it's because of this theorem. Okay, so let's prove this. So we know that for sure. Remember that in our input we assume that for each u, v, z, we had that the cost of going from u to z is always lesser equal than the cost from going to u to v plus the cost of going from v to z. And this is exactly what we did when we took the shortcut. So we know that instead of doing this thing, we did this thing. So we took a shortcut. And from this hypothesis, we know that taking the shortcut is always a shorter path than doing the original thing. So because of this, we can easily say that basically that the cost of our Hamiltonian cycle H is for sure, because of this hypothesis, is lesser equal than the cost of E. Where E, remember, is this thing is the Eulerian tour. So because we took shortcut, we know that we used less fuel, let's say. Okay, but what is the cost of E? So the cost of E is pretty easy to compute because it's actually twice the cost of the spanning tree. So it's actually twice the cost of T star. And this is because we doubled the edges on the spanning tree. So that's always true. Then another thing that we can say is that in this graph we have 1, 2, 3, 4, 5 nodes. Okay. So our, let's say, optimal Hamiltonian cycle will look something like this. Okay. So if we remove one of these edges, what we end up with is a spanning tree, because it's a tree that covers all of the nodes of our graph. So if you look at these nodes, these are all of the nodes of our graph, and without this, so I will just delete it for a moment. As you can see, this is a spanning tree. So let's call this spanning tree T. We know for sure that this spanning tree, so the cost of T, is for sure greater or equal than the cost of T star. And this is because we built T star as the minimum spanning tree. So we know that the cost of T star is the minimum among all of the possible spanning trees that we can find in G. Okay, so that's our that's another thing that we can say. And obviously, another thing that we can say is that for sure the cost of H star is lesser or equal than the cost of H. And that's because obviously we are the H star is our optimal Hamiltonian cycle. So now we can sort of put together all of these things. So we have that the cost of E is exactly twice the cost of T star. Well, actually we don't need this. So we don't need this. What we need instead is that the cost of T star, so the cost of the minimum spanning tree, cost of H star, so cost of the optimal Hamiltonian cycle is for sure greater or equal than the cost of T. And that's because we obtained T by removing one edge from H star. Okay, so that's it. Sorry for that. Now let's put together everything. So we have that we can write that the cost of H is lesser or equal than, instead of writing the cost of E, we write twice the cost of T star. And now instead of the cost of T star, we can put something greater than it, so cost of T. But we know that cost of T is smaller is smaller than the cost of H star. So we can write that the cost of H is lesser or equal than twice the cost of H star. And as you can see now, we can divide by the cost of H star on both sides, and we get the cost of H divided by the cost of H star is lesser or equal than 2. And this is what we wanted to prove. So this was our theorem, and we proven it. Okay, so that's it. This is the proof. So we prove that in the worst case we get a tour that is like twice as long as the optimal tour. Now we've just proven that the cost of H divided by the cost of H star is always lesser or equal than 2. This is a horrible 2. Okay, so, but this is a general analysis that we did. So we've taken an algorithm, we analyzed it, and we sort of somehow proven this. But we don't know if this analysis is tight. So what I mean by that is, like, for example, considering this rule, it might happen that instead of 2 here, like if we might find that actually this is not a 2 anymore, but it is like a 1.9, for example. Like there's we haven't found let's say a rule that says that it is for sure less or equal than 2. Like we're not sure 100%. The only way to be sure that this rule is tight, so that in every case, in every possible case, this factor here is less than 2, is we need to find an example in which the cost, like this factor here is exactly 2. And in that case, in that case we found an example that proves that our rule, so the rule that we sort of derived from the algorithm, is tight. So we are sure that it is, let's say, precise. So how to do that? So as I said, we need to find a bad example for our algorithm. And in this case, the bad example looks something like this. Okay, so imagine a graph like this, and remember when we're working with TSP, we are working with complete graphs. So in this case, I haven't drawn all of the edges. I've drawn only the edges that cost 1. Assume that all of the other edges that connect the rest of the graph have a cost of 2. Okay. So for sure, it's pretty clear that our optimal Hamiltonian tour looks something like this. So we put these nodes here. So the optimal Hamiltonian tour is just this, right? It's kind of clear. All of these has cost of 1, so the total cost is n. So where n is the number of nodes. But what happens when we apply our algorithm? So our algorithm, as the first step, finds the minimum spanning tree. So the minimum spanning tree of this thing is just this sort of star. So because it is the tree that covers all of the edges, all of the nodes with minimum cost. And now what we do, we double the edges, if you remember, like this. And now we have to find the Eulerian tour. So the Eulerian tour, let's say that we are visiting this node first. So let's call this node A, then we want to go to B, then we go to C, then to D, then to E, then to F. Let's say that our Eulerian tour that we find sort of visits these nodes in this order. So what our Eulerian tour will do is it will go there, then it will come back to A, then go to C, come back to A, go to D, come back to A, go to E, come back to A, and go to F, and go back to A. Okay, so kind of easy. What's the problem now? Now, if you remember the algorithm, we have to use shortcuts to sort of skip edges that we've already seen, skip nodes that we've already seen in the tour. So what actually happens here, let me redraw the thing so that it's a little bit more clear. So the first thing that we do is we go to B. Okay, that's okay. So let's go to B. Let's use another color. Now, what we should do is we should go back to A. So our Eulerian tour would say, okay, go back to A, but we cannot go back to A because we're already visited that. So we have to go to C directly with a shortcut. Okay, so now from C, it's the same reasoning. So we should go back to A, then go to D, but we cannot. So we use a shortcut to go here. Then to D, it's the same. So we go to E with a shortcut. Then we go to F with a shortcut. And then from F, we can actually take this edge and go back to the beginning. And this is our cycle. This is the cycle that our algorithm finds. How much does this Hamiltonian cycle cost? So if you look at it, we paid 2, because remember, I've drawn only the edges that have cost 1, but remember that all of the other edges have a cost of 2. So all of these, let's say, wiggling arrows that I've drawn mean that we have to take an extra edge that is not here, so it costs 2. So basically we paid 2 to reach every node, except for the first node that we visited, which we visited with a cost of 1, and let's say the central node that we visited from the last one, which also we visited that with a cost of 1. So in total we paid 2n minus 2. So this is our cost. But if you look at our original cost, we paid n. sort of the optimal cost. So if we do the limit from n that goes to infinite of 2n minus 2 divided by n, this thing is 2. And this proves that our analysis here is, let's say, tight. So because there is this, theoretically, there is this unfortunate, unlucky example that that makes our algorithm not very effective.